Okay. So why is this important? Well, this says how much the solid is changing, or the volume of the material is changing over time. And this second term here has to do with the fact that the body is rotating. So if I didn't have any rotation, I wouldn't be able to generate any pressure in the fluid. Okay, so it's really important that we have this term that accounts for the fact that the material is rotating about a fixed point. Okay. So now we've defined our equations. We need to set up a series of boundary conditions that let us solve the problem and represent what's going on in a natural joint. And really, most of this is quite straightforward. We constrain the body so that it doesn't fly off when I apply a load to it. But really, the important thing is to look at the boundary AB at the bottom. So we account for contact mechanics, because this boundary is being pushed against a hard surface. And if it was just a solid material, that would be the type of contact pressure that you need to keep them from touching. But we also have a boundary condition that's applied to the pressure, which is this lubricating pressure, which I'll come on to talk about in the next couple of slides. But really what's important here is that the backing, DC, is impermeable, and that represents where the bone layer is. The sides are just considered to be far enough away so that we can have zero stresses and zero pressures. Okay, so now I'm going to talk about thin film lubrication, and this is really the part of the problem that's the most novel. So on that boundary, on that AB boundary that we were talking about, we solve this equation in addition to the other equations that we're solving. Okay, so it's just a boundary value problem, or a PDE problem on the boundary. And these two terms here are, again, left-hand side of the equation is what we could call a classic lubrication theory. Okay, so lubrication theory takes a fluid flow equation, Stokes flow, for example, and then assumes through that very thin film that everything is constant, and then we integrate those equations over that constant over that film, and we can obtain this equation. This is known as Reynolds equation without this thing on the right, and that is the same Reynolds as your Reynolds number, but a very different application. Okay, but the key thing here is that we have an additional source term. Okay, and this source term controls the flow into and out of the poroelastic material. Okay, so where V is positive, flow is going into the material. Where V is negative, flow is coming out. And that's really the novel part of this type of model, is that we're accounting for the fact that we can have flow into and out of that region. On the right-hand side, you'll see an equation for this parameter Q, which is our lubricating flux. And this depends upon H, okay? And H is the separation of the two bodies, so of the poroelastic material and the impermeable surface. And again, you can see that that also includes this value U, which is the rotation, the tangential velocity, that's the word, of the material in the interface. Okay, so without any velocity, we wouldn't generate any pressure. But importantly, with this term switched on, we can solve for this P lubrication, P lub parameter, and then that couples back into our poroelastic model to provide the lubrication to the material. Okay. So we are able to measure the flow into and out of the material using this parameter V, okay? And these are just a series of integral terms that let us measure the amount of flow. And this is quite important to our problem because we have a rotating body against the surface, and that rotation, or the direction of that rotation, may change. Okay, so when you're walking, it goes one way and then it comes back the other. So we like to look at these terms because it tells us about whether flow is being moved into or out of the contact on the positive side or the negative side. Okay. We also have a load that's generated. So because the region is lubricated and in contact, we generate solid stresses and fluid pressures. And if I integrate those over that boundary, then I obtain the total load that they apply to the boundary. And that load needs to match to a certain value of the displacement. okay, which is the equation on the right-hand side. So if I push my material further in, I generate a bigger load, and I want that load to match a specific load that comes from the gate cycle, or comes from standing still, for example. Okay, so this equation allows us to solve for a specific load on top of the other equations that we're solving. Great. And then we can also measure friction. So it's tribology, we're always interested in friction, and these equations allow us to do that. So once we've solved the problem, and we have our pressure field and our displacement field, we can then post-process that data and calculate the traction forces. So these are the tangential forces in the contacts, from which we can then calculate a total coefficient of friction for the problem. Okay, we do have some adjustments we have to make with certain terms in this equation, because we have films that are vanishing. Here's a list of operating conditions. I'm not going to go through them all. What this is trying to show you is there's a lot of input parameters to the problem, not just from the geometrical side or the operating side of the problem, but also material parameters. And most of these come from literature, where people have extensively studied cartilage, looking at what the viscosity is of the fluid, what the compressibility of the fluid is, the solid behavior, the material properties of the solid, as well as those about the of the poroelastic matrix. Okay, so that includes the permeability, for example. And we assume to start with that it's an isotropic material, and anisotropy is something that we can build into this later. So this is just a bit of a summary. So this model is set up and solved in a bit of software called COMSOL Multiphysics, which was useful because we can play around with the inputs and outputs quite readily. So again, an idealized model. But in order to get to a problem which is fully transient, so time dependent, we have several steps that we use to build it up. So this is just explaining that it's not a case of just solving all the equations. It breaks if you try and do that. So we need to slowly evolve the solution towards one that can work. And what's important here is that when we get to number 3, we have a steady state solution, which includes the lubrication, the solid mechanics, and this load that we want it to match. And then we can use that to look at time-dependent problems. Great, so here's some initial results for the steady state problem. And this is at a specific load and a specific sliding speed or rotational speed. So the important thing to notice is that the highest stress of the material is on the backing of the cartilage, which is where the bone connects to the cartilage. So yes, the model doesn't include the bone. We assume that that's a rigid layer and that would move in reality, but this has allowed us to look at that. And it's well known, if you go and do MRI scanning of someone who's standing still, the maximum pressure is always on the backing of the cartilage. So that gives us some confidence this is working properly. The other thing is that we have this pressure distribution. And you can see that the pressure reaches a maximum value in the middle of the contact, which is what you would expect because they're being pushed together, and that's where the highest displacement has occurred. And again, that brings us some confidence that the model is working correctly. So this looks in a little bit more detail at that interface. And you can see here that the lubricating pressure, P lub, is actually bigger than this contacting pressure. Okay? So importantly, in a steady state problem, we now know that the maximum pressure in the fluid will be higher than the solid stresses on that interface, which is quite interesting. The other thing to look at is this graph on the right, which is quite an informative graph when you're a tribologist. The key thing is if we look at this parameter Q, this is the flow rate of the lubricating flow, okay? And remember this part here is where these parts are non-zero, so that means it's in contact there, or the films are very small, and you can see that the flow rate comes down to almost zero. Well, it is zero in this middle bit, which means there's no flow going through the lubricating region. What happens instead is that the flow is absorbed into the material and then pushed out the other side. So the fluid is being moved into the material and then out the material the other side, which goes back to that image, that schematic at the beginning that I showed you. So it's really interesting here because the flux is 0, but we still have a positive pressure. We can then look at, this is called a Strybeck analysis. It's a very technical tribological problem, but what this is really saying is what is the regime of lubrication. Okay, so lubrication has several regimes. If your surfaces are very far apart, there'll be no displacement, and that's called hydrodynamic lubrication. As they get smaller, they start to deform. That's called elasto-hydrodynamic lubrication, where you have some separation of the bodies. And then we move towards one where they're fully in contact, and that's called boundary lubrication. And this graph is quite interesting because what it shows us is that in a conventional contact, we would have this transition point here where we move towards the boundary problem much earlier. So this is delaying the transition to the higher friction regime. Okay, so you get high friction where you've got lots of solid on solid contact, and where you only have a fluid film, you have lowest friction. And this is the same location as here. So here, the bodies start to touch. And after that point, your friction increases. So again, this is giving us some insights into what the friction behavior in a poroelastic type problem looks like. Okay, but this is steady state. So this assumes that we're working at a constant speed and a constant load, which is not true in a natural joint. So this is just a mock-up of what would happen in this type of problem if you were able to analyze it under steady conditions. So that then leads us to looking at the transient problem. Okay, so to do this, what we did was we looked at solving the time-dependent problem for several cases. And they have some different variations of either the load that's applied or the speed at which the fluid of the bodies that are moving. Okay? And some of them are sinusoidal, and some of them are constant, so it's just looking at different combinations, whether your load is varying over time or your speed varies over time or both. And then in this last case, case 5, we've tried to simulate what a gate cycle might look like. So where you have a certain shape to the load profile that links back to biomechanics, and where your speed is also varying in a nice way. But the important thing to say is that these are just inputs. So you could have a numerical description of load and speed varying over time. It wouldn't matter. You'd be able to map that behavior onto this problem. Okay. So this is the first case that's of transient that's important. Here, the speed of the problem is being held constant, and the load is varying sinusoidally. So it's rotating constant this way, but the load is being varied up and down. And you can see as the loads increase and decrease, that we generate stresses and pressures, but note that the pressure changes a lot faster than the stress does. The fluid response is faster than the solid. And that's confirmed by this graph down here, which shows you that the fluid load that's carried by the fluid pressure varies a lot more. So it increases a lot more, whereas the solid is actually it's not constant, but it's not varying anywhere near as much as that fluid load is. This graph here links back to that slide I had around whether the flow is moving into or out of the contacts, and on which side. So whether it's on the left or the right-hand side. And again, this is giving us some really interesting insights because 2 of the curves are almost constant, because they're saying that there's no absorption into the material from the left side, from the right-hand side of the contact, whereas on the left-hand side we have these very dramatic changes of fluid being pushed in and pulled out of the material based upon how this load is changing over time. And that's also useful for looking at, say, the friction coefficient in that bottom right diagram. Okay, so again, this is where we have the load sinusoidal and the speed constant. Case 3, this is where we have the speed changing for a constant load. And you can see the pressures and the stresses are changing a lot less. And that's because the load is constant, but the speed is changing. And you get these peaks and troughs of the material, of the loads over this time period. The friction is almost constant because it's just the speed that's changing. But we have quite a dramatic shift in the shape of this fluid flow graph in the middle. We have fluid being pushed into one side of the contact and pulled out of the other. And then as soon as we reach the next cycle, or halfway through the next cycle, that whole system of equations is almost completely reversed. So where the black line and this dotted line are switched over, which says that exactly the same flow goes in one way and then comes back out the other. Case 4, this is where they're both sinusoidally varying over time. And this is starting to become a little bit closer to reality in terms of walking. And you can see quite clearly there's a very complicated interaction here. Your pressure changes very fast, whereas the stress is quite constant. And again, you can see that in this graph here, where we get this big change in the load obtained from the pressure, whereas the load obtained from the solid is very small. And it's quite interesting if we look at the friction graph, which is being generated, so that's dotted line. We get big changes in the values of the actual friction coefficients when we start looking at both speed and load varying with time. And now the most interesting case, or the most relevant case to biomechanics. So this is our gait cycle representation. So you can see that the black line here has 2 peaks, which kind of represents what happens in a hip. And then it's very flat, so it's almost constant here. Whereas the speed is varying sinusoidally, so it's kind of walking, and you get these peaks and troughs. But what's really interesting here is that, again, if you look at the 2 colourful images, you'll see that the pressure changes very fast. Yeah, it's changing really, really quickly, whereas the stress changes slowly, and it is only in this region where it is constant that the stress actually starts to relax down towards 0. And you can see that in this graph here. Again, this is where the total load of the fluid and the solid are being output, and this fluid takes the load. So as I walk, the fluid is the thing absorbing the load, whereas the solid is almost constant. And only when I have this period where the load is quite constant does the solid actually respond. And again, if we look at friction coefficient, this is now really complicated, this response. It's flow is moving into and out of the contact on each side of it, depending upon which part of the cycle you're in, and then you get these quite complicated changes in the friction coefficient occurring across one cycle. And this is insightful, because if you ask a clinician, what's the friction during walking, they'll give you one number. And that's not true, because it varies over time. And it varies dramatically. Big changes from almost 0.1 to almost 0.4, which is big. So that was a bit of the work that we did with 2D models, and then that's been advanced towards this type of problem, which is a bio-inspired bearing. And this is some work I did with Imperial College in London. And really what they were trying to do is design a bearing that has this same load carrying capacity. And we used exactly the same techniques, but we've expanded it into 3D. This is using a different bit of software called Phoenix, which is an open source finite element code. And here we're looking at the effect of the permeability. And the permeability affects the amount by which it's easy to push fluid. And what we see here is that as the permeability decreases, we get big shifts in the amount of force and the amount of pressure that's actually generated within the contact. So these are some results from that study. We've also gone to look at what happens if you have 2 poroelastic bodies touching with lubrication. And this is much closer to the real joint problem. So any real joint has 2 interfaces with cartilage touching, and having established what happens when you have cartilage against a hard, impermeable surface, we're now able to look at one where we have 2 poroelastic media touching with lubrication. And again, this is a Strybeck type analysis, which is steady state, just to try and understand what happens in this type of problem and how it differs to one where we don't have an impermeable surface. And again, what we see is we have this delay in the transition towards this regime where the friction starts to increase. And this is kind of work in progress, and you'll see some more of this as I get to some of my later slides. So a bit of a summary of this bit of work. We've developed a poro hyperelastic model and solved in a simple 2D geometry, which represents a mock-up of a natural joint. The model fully couples together solid mechanics, fluid mechanics, and lubrication in order to understand what's going on. And this has indicated some of the mechanisms by which fluid is transported over the contacting interface, and in particular, whether the solid or the fluid phase is carrying the load. The fluid responds much faster than the solid, and when the solid is greater than the fluid in terms of the load, flow is moving one way or the other. Okay? So some of the more recent developments include these 3D solutions and bio-inspired type bearings. So there's plenty of future research to do in this area, particularly around trying to make sure we describe the materials of cartilage in an accurate way. Viscoelasticity, anisotropy, swelling, and other parameters that may come into, say, longer time period type simulations. We also want to include surface features. So in tribology, in conventional machine elements and bearings, you have lots of surface features, roughness and textures and other things, and they significantly change the frictional behavior of the contact. And here, this model assumes everything's perfectly smooth, which again, in reality is not. If you go and measure cartilage surfaces, they'll have a particular type of roughness, which needs to be accounted for. There's some work to do on actually the equations we're solving, which I'll talk about in a couple of slides' time. We also have the fact that this material, that we're using a continuum model to describe these mechanics, whereas actually, if you look at cartilage under a microscope, it's very non-continuum. So it's made of fibers and fluid, and there's some scope to look at some multi-scale modeling of this type of problem, which again I'll talk about soon. Experimental validation is a tricky one. We have lots of expertise in my school of doing experiments for sort of biomaterials where we do indentation testing and other things. So we need to take what we can learn from those types of problem and then apply them to this bearing. And that then might link into this kind of clinical relevance of the model, in which we can use some of these outcomes to determine strategies for treatment, or by changing the material properties or adding implants of scaffolds or injecting fluids into the model, we can see what their effect may be on the long-term health of the joint. Excellent. So now I'm going to talk about some of the work from my PhD students rather than my research. And I mentioned this in the previous slide. This is my student Craig's work. And this is looking at the actual mechanics of the equations we're solving. This is very mathematical. But if you look at the state of the art of cartilage models, they're well established in this biphasic theory, which is this coupling of the fluid and solid, which I've been talking about. But the derivation of those equations from first principles is questionable. Okay, they're based on what we call biot theory, which is, again, is a geomechanics type model used for soils and sands and other things like that. And if you follow the derivation, they make lots of assumptions which may not be so applicable to biomaterials, particularly in cartilage. So we wanted to look at this in a bit more detail and to see whether we could expand the equations that we're solving in these models and bring our responses that we see closer to reality. Okay, so constitutive models for cartilage is a big area. There's lots of people working on this, and they work on it in very different ways, depending upon the type of time period of which you're interested in. or whether you even care about there being a fluid in there. So lots of people, when they model joints, will just assume the cartilage is a soft solid. And they don't model lubrication, and they don't model the fluid flow aspect in any way, which, depending on what you want to measure, might be okay. But what we were interested in was really understanding the equations of these materials so that we can map them to the outcomes of the other models that we were talking about. Okay, so biphasic theory kind of sits in the middle here, and you have anisotropy and all sorts of other types of model. Fiber reinforced or fibril reinforced models are one of the most common that are used at the moment. But realistically, there's gaps in here because they all rely on the same theory, but that theory has problems. And that is dictated by this horrendous slide that I did ask my student to try and make more easy to understand. But basically, we have these equations here and these equations here. These are the conventional equations you would obtain from Biot theory if you followed through the poroelastic description of the fluid. But then we have 3 extra terms, okay? And these 3 extra terms are introduced because we've not neglected certain aspects of the mechanics. So the first one is the coupling of structural inertia and volumetric strain. Okay, and what do I mean by solid inertia? I mean the rate of change of displacement with time. The second comes from compressibility, okay? So if I have a compressible fluid, I'll end up with another term, which has the actual compressibility of material in there. And then there's another term here which has to do with inertia and pressure that are coupled together. And Biot theory neglects these, possibly because he didn't want to write this equation down when he was trying to derive it, but also it simplifies the expressions you're solving. But fundamentally, what we wanted to see is, do these terms make a difference when we're looking at cartilage in a problem where you have loads and speeds varying in a gait cycle? So a 1 Hertz loading. And, well, I'll go on to show you in a minute what happens. But it's a very simple model. We take what we would call like a cartilage plug. And this is useful because this is the same type of geometry they use in the lab to do indentation testing. And again, simple mesh, simple problem. And we solved this in another open source software called OpenFoam. That was my student's decision, but it made his life more difficult. But you know, we've come out with some really interesting outcomes. Again, we set this problem up. We're just going to compress the top of it, and we stop flow from leaving this material elsewhere. We use very similar material parameters to the other model well established in the literature. So you can see here, it's the time-dependent model. We get this pressurization of the material over time. But really, this is the most important outcome. What this shows is that if you add these extra terms, that you get significantly different values of the total force that's applied in a given time period. Okay? So here, we compress our material and hold it. And what happens is the fluid responds really fast to that load. The solid takes some time to build up. And actually, the peak pressures that you obtain are quite different if you do include these extra terms. So as I include extra terms, I start to shift the maximum pressure up, and I start to push the solid response further to the right. So what this really showed was that when we're considering this type of time period of loading, so a 1 second time period with a compression of about 10% of the material, that we do indeed need to include these extra terms to have an accurate description of the response. And that was an interesting outcome because if you read the literature around cartilage or around poroelasticity, this is never mentioned anywhere, mainly because they just look at an equation and use it rather than question where it came from. Okay, so what we're trying to do, or what we've been trying to do with this bit of work, is just progress towards a complete understanding of the mechanisms by which continuum poroelasticity are derived. We obtain extra terms in our governing equations, and these can account for significant differences in terms of the actual loads and speeds that are carried. There's lots of capacity to link this with further developments. So, for example, some of the biological behavior, swelling, looking at, say, the viscosity of the fluid and the complexities of modelling synovial fluid, which is very non-Newtonian. And that's really where this bit of work is leading in the future. Cool. So now I'm going to talk about another PhD student of mine who is looking at multi-scale modelling of poroelastic cartilage. This is a very challenging problem. What are we trying to do here? Well, we're trying to couple an immersed fibrous network model, which I'll talk about in a minute, with this continuum poroelasticity model to derive what we call a multi-scale model of articular cartilage. So cartilage is complex because of this separation in length scales. If I look very down under a microscope at the cellular level, I have these fibers and their entanglement. And then as I scale up, you can start to see a structure of those fibers, and then it becomes the joint, and it becomes the material, and then it becomes you and your overall ability to move. So this is really quite difficult because what we model in a continuum type model assumes that it's consistent. The material is just a solid with some fluid inside of it. It doesn't have any information about this fibrous interaction. The way that we account for those is through the stiffness tensors and the permeability. These are the material parameters of the model. And you should be aware that some of these are what we call intrinsic material parameters. They're not really properties of the material, it's an assumed behavior of what happens at a different scale. So this project aims to couple the microscale model with a macroscale model, so models at different scales, to map pore scale effects onto the material response. So just talking about this in a little bit more detail, again, the fibers that make up cartilage are on the scale of 0.1 to 1 microns, whereas the joint itself is 1 to 10 millimeters. Okay, so if I wanted to model all of these fibers in this problem, it would just be intractably large. So what we want to do is we want to average what goes on here and use it in here. I say average, the word is really homogenize, but we'll get onto the detail of some multi-scale mechanics in a minute. But really this is a difficult problem because the material varies quite a lot. You can see here that the fibers are arranged in different positions. But this lends itself quite well to what we call a immersed fibrous network model, which is what I'll talk about on the next slide. So this is some work that one of my colleagues in computing is doing in Leeds. And realistically, what is it? Well, it's a series of connected springs which are in a fluid. And these springs have different stiffnesses and orientations. And this is one way of representing how the fibers within cartilage may interact. And the important thing is that we can solve this spring deformation with fluid flow using this type of model. And what we want to do is use this to describe the behavior of the poroelastic material at this small scale, and then average over that response and use it to drive the poroelastic behavior. Okay, so again, we can get some really quite good detailed images and understanding of what cartilage looks like under microscopes, and use this to link to the fibrous network modeling. So you can see that there's a clear link between, say, imaging and the composition of those multi-scale models that we're going to use. In particular, orientation, thicknesses of fibers and their stiffness, and you'll see that we can use those as inputs to the model. So, what do we want to do here? Well, what we're trying to say is that we're no longer using this continuum poroelastic description. Instead, every single point in our model is a separate simulation. And this simulation is periodic, okay? So that means that they're repeated up, repeated sideways. And if I average over that, then I can take that averaged value and use it to represent this one point in this other model. But the parameters that drive this model are the same as the outcomes from this. So data has to go here, 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 here. It's complicated. But we use something called homogenization, which basically averages this periodically repeating simulation and use those to drive the values of this type of problem. Okay, and this is kind of a bit of a mock-up of what that looks like. So we solve some equations here in our joint model. We then have this separation of scales. So we're saying that this point can be represented by this type of smaller simulation, which becomes this fibrous network model with appropriate boundary conditions that let us have pressure gradients and strains applied to our network, our spring network model, and then we average those to obtain a new functional relationship for our stresses and flow rates, which we then pass back into here. And the whole thing is fully coupled. And this is really moving beyond the description of cartilage using a continuum type model. Okay, so what my student is doing at the moment is trying to represent some of this by using some simplified versions of these models, just an indentation test, where we've taken our understanding of cartilage, broken it into what we have as a continuum model, coupled to a continuum model, and then eventually we'll couple that with our fibrous model. Okay, so the first thing to do was to make sure that we could have the mechanics make sense before jumping into the fiber stuff. So this is some initial results where we're solving the same equations at both scales just to make sure that we get the same behavior back out. And what we do is we solve these traditional biop type terms for our material, poor elasticity, and every single point in this simulation is represented by a different simulation at a different scale. And again, we then average over these, or homogenize, and use that data to drive back into our other scale. And the solution procedure is pretty complicated and pretty time consuming. And we have lots of parameters moving around in our model. But what we effectively have here is we need to pass data to this small scale where the fibers are, and then pass data back to the macro scale and increment in time. So these are just some initial results, and these show that we're actually getting very small differences between just using a single scale model and one where we've separated out the mechanics. And they match identically to what you would get just using a one scale model, which is great. So the next step for my student is to start to develop integrating this fiber model into these responses. Oops. Cool. So this is what the fiber models are going to look like once we get to this stage of the problem. This is our Stokes flow type model with this equation here that represents the effect of the springs within that material response. And you can see here that these springs are all interconnected here, and the arrows represent the motion of the flow within those domains. And what we're going to do is we can then average the flow effects and the pressure effects in these scales to drive back the values that we need for the macro scale model. And one thing that's really nice here is that these springs can be defined how you want. So I'll talk about that in a second, but we can tune what we want our spring models to look like and what we want them to do in order to get a better understanding of the material. Okay, and then obviously some experimental testing, because we're looking at this type of plug problem. We're going to do some experiments where we can make sure that we're matching to what we get in the lab. And then we can tweak and tune our parameters in our models in order to meet those conditions. So one thing that's really important in cartilage is that we have these different layers. From the layer that's in the contact on the lubricating region all the way through to the deep zone that's kind of connected to the bone. And one thing that's really useful with our multi-scale model is that we can represent these different layers by changing the springs and their stiffnesses and their orientation. And this is really advantageous because in a continuum model, that would only be represented by anisotropy. But we can't make sure that the anisotropy lays up with these, because if I want to look at cartilage and I want to try and measure the anisotropy of these different things, it's pretty difficult to do. Even if I say, take my cartilage sample and chop it up into sections, I then destroy the fibers, so it no longer behaves like it would do anyway. So this is really useful, and it's something that we're looking to do, is to use this sort of zonal structuring in order to analyze this material. This is also going to lead on to looking at gait cycle analysis, as we have done in the previous models that we looked at, as well as damage. And this one's really important, because we can take these springs and just either they are there, they're not there, or we can build in some algorithm that says if you reach a particular stress or force, then the spring breaks. And that can be useful for looking at things like fracture mechanics and other types of degenerative conditions. Great, so progress towards a multi-scale model for cartilage has been made, and we're currently looking at a continuum model, but we're trying to verify this and then move on to a fiber continuum model in the next few weeks and months. We want to look at zonal structuring, gait cycle analysis and damage modeling in this project, and this really has lots of potential to include other types of interactions which are occurring at this smaller scale, such as disease progression, remodeling effects, and again this kind of homogenization methodology that can be applied to that with this rigorous mathematical derivation. Great. Yeah. I'll go quickly through this one. Okay, so I'm also currently supervising a postdoc, Basil Matai, and his project is looking at avascular necrosis. Okay, and this is a degenerative bone condition. It's very prevalent in poor economic countries. And what it does is it eats away at the bone and deforms the bone to such an extent where the joint stops working properly, and then you need a joint replacement. And it's a very bad problem, where if you don't intervene early, you're going to need a joint replacement. And that's bad, because expense and pain for patients, etc. So AVN is a condition that eats at the bone behind the joint backing. So it's not the cartilage itself, but it's the bone behind that. And you can see as the disease progresses in time, we change the shape of the joint, and then it completely stops operating like it should do. And this is really, really challenging, because it's for clinicians, they have no idea how this thing progresses and why it progresses as it does. They know that it has something to do with the loads and speeds applied to the joint, but they haven't got a model, or at least a kind of mechanism to describe this. And if you look at what happens to the joint, it's probably best represented on these bottom two images. You can see this is a healthier joint. And then this bit's healthy, this bit's necrotic, and then over time the necrotic material spreads. And what happens is that this surface at the top, which is your contacting interface, is smooth here, and then it completely breaks up here, and the joint stops working. And it's really, the patients with this can't even walk. Okay, there's a lot of work in the literature around the mechanisms by which necrosis occurs, the interaction of the biological materials and how that's all mapped out. They've got a pretty good understanding of it, but what they don't have are models that are able to kind of deal with this. There has been some work looking at the progression of this, but it's not linked to the joint. So what we want to do in our project is take our model of the cartilage on cartilage for the type of joint, have some nucleation of our disease, and then model the progression of that disease as it grows and the effect it has on the shape of our joint. And then look to see whether we can identify critical failure or where surgical intervention should be made. Because again, surgeons disagree about should you do it at stage 1 or is it stage 2, when's too late. So this is what our current development is. Basel only started about 3 months ago, so this is already quite good progress. But you can see we're adding the bone backing into our model. And then we're going to seed our necrotic region, link it with some disease modeling, and then have it grow and see what the effect on the overall joint mechanics is. So some progression. Again, this is your cartilage on cartilage type problem, and we're just developing some of the tools we need to make this work. We've also looked at some 3D problems. This is work in progress. This is just a nice mesh of what it might look like in the future. Okay, so we've made some good progress towards modeling natural hip joint in healthy conditions, and then we want to add in our AVN and look to see how we can couple this type of tribological simulation with one that's more biologically relevant. We want to use disease progression modeling to link those stages with the joint health, and then we can look at intervention modeling such as scaffolds or fluid injections and see how they would affect this degenerative condition. Okay, so in Leeds we're developing, or I'm developing a range of different tribological models for looking at the natural joint. This has been computationally done, but we're looking to do a lot of experimental validation with my partners in Leeds. We've had some specific focus placed on poor elastic material models and the sort of underpinning fluid structure interactions. And what we want to do is link these models of healthy joint operation with degenerative conditions, and then these sort of long-term biological interactions such as bone remodeling and disease progression, etc. So this is where I'm trying to get collaborations with Cleveland universities, because we have a lot of common themes in these areas, and I'm hoping that we can make something of that. So thank you very much for listening. I must say, special thanks to all of my PhD students and collaborators, so thank you very much.
Thank you. ¿Alguien tiene alguna pregunta? Casi la tengo en español, ya la puedo traducir, pero ¿alguien tiene alguna pregunta? Profesor Diego. Sí. Bueno, tú la puedes, bueno, hazla. Sí, sí, puedes hacerlo. Sí, claro que sí. Pero hazla en español para que entiendan todos. Sí.
¿Tú la traduces?
No, tú la puedes decir en español y en inglés.
La pregunta va en torno a la colocación de las resortes en la malla. Y cuando uno coloca los resortes en la malla, normalmente el problema queda dependiente
de la geometría.
Pero es un problema malla dependiente. Entonces la pregunta es, ¿cómo se podría solucionar esto en el futuro? Yo creía que podría hacerse con un tensor. The question is that when you put the links into your mesh, you have a mesh dependent problem. That's the main problem with these kind of things. Probably you can move the solution of this problem from the links to another kind of tensor that can represent the orientation of the collagen and other fibers. Yeah. What is your idea? I mean, that you have proved the mesh dependency in your problems? In which problem?
The last one, the problem when you have the springs.
Ah, yes.
Yeah.
Good question.
Here.
Yeah. So it's going to be quite hard to do. And I think one of the things we need to do is look at what we can measure in the lab and then try and link it back to what we have here. I'd say you're right, we have this kind of discrete representation of this continuous material, and that's pretty tricky to do. I think what we may end up doing is changing stiffnesses within our model and the orientation of that in order to represent the layout.
I can do that because we try to do that the same problem with the links in the test. And what we learned to us when we simulated the paper, okay, that's good, it's a good idea, but sometimes we have the problem like if we measure the things and you need to avoid these kind of things.
Yes.
Yes, that's good.
This is the interesting one. So these fibrous models, they do work as a point-wise representation of what's going on. So it may be the case that we can change the size of our strings to add more mesh points to maybe.
La otra pregunta es acerca de la localización o migración de la zona vascular. Puede ser dependiente no solamente de la carga mecánica que hay sobre la superficie, sino además de las condiciones de contacto de las células que están ahí con el resto de las células que están dentro del hueso. Entonces, ¿cómo puede incluir el modelamiento de esa
de distintas localizaciones?
Another question is about the avascular axon that happened there.
And the last one.
Last one. Yes.
Yes.
Because, of course, there is a problem with the contact mechanics. Contact mechanics probably transport the energy and the mechanical loads to the zone. But, of course, there are another kind of biological conditions that could allow the diffusion of some biological processes, molecules that can produce the nucleation can go in time. So you can include that into the model.
I think what we'll probably end up doing is having some species transport type problem, where we may have some far away, some source, which is then how is it being received in the necrotic region, and whether the mechanical loads and speeds change that supply, which then may instigate the nucleation and then the progression of the disease.
Si nadie más tengo, yo voy a hacer una pregunta más para que puedan irse a clase los que quieran irse. I have another question. So, lo voy a hacer en español. I'm gonna do in Spanish first. Mi pregunta está relacionada con el primer modelo en el que hay una frecuencia. La pregunta es si esa frecuencia primero está relacionada con la frecuencia de carga o es una frecuencia de respuesta del modelo y ¿cómo afectaría la variación de esa frecuencia en el modelo? So my question is, you have a frequency like 1 Hz at the first one of the parameters that you have in your first model. So my question, this parameter is about, in the first model, is about is the parameter of the model or is a parameter of the force that you are giving maybe when you are representing the gate cycle?
These cycles.
Yeah.
Yeah, so it can be anything. So these are, I've got nice smooth equations, but you can put whatever profiles. So one of the things I would really like to do is move this towards non-conventional cycles, so jogging, or which would be a faster one, or standing for a long time and then moving, which would be probably a longer time period. Obviously, the longer the time period, the more computationally challenging it becomes. So, I mean, this simulation probably took 8 or 9 hours. And the gate cycle one, which is really challenging at these big shifts, takes even longer, 15 hours maybe, because these sharp changes just require the model to have those small time steps. But if you were to look at something over a longer time period, it's an input. This is an input to the model, so it's a time-dependent model input, and this could be replaced for a different gate cycle, depending upon the joint times.
So then, any frequency that you put in this input information will give you the same repetition of the cycle. It is not considered that maybe with this frequency that could be considered into the model, you can have another response, maybe for damage or something more that is taken into account.
It would be, what you would need to do is find some way of linking the outcome from the model back to changing this.
Okay.
So maybe there's some decay linked to this, so your peak loads may move down. Yeah.
Lo que preguntaba entonces era yo que si se podía cambiar que si esa frecuencia era considerada dentro del modelo o simplemente era la frecuencia que representa la marcha, por ejemplo, que es un hertz, y si hasta ahora esa frecuencia es un punto de entrada, pero esa frecuencia podría, si se considera dentro del modelo, cambiar estos ciclos que no darían siempre el mismo máximo. ¿Sí? Más o menos eso es. So, thank you very much. Thank you very much. Gracias a todos, muchísimas gracias. Hay una pregunta acá.
Bueno, mi pregunta es más como la generalización que se hizo, digamos, para los modelos, pues, o sea, no estoy segura si eso se hizo en base a algo ideal o un porcentaje promedio, digamos, cómo sería la estructura de una persona, ya que hay varias, digamos, alteraciones en cada persona que se podría tener en cuenta y que podrían variar, digamos, los resultados de las simulaciones. Entonces me gustaría preguntar con respecto a qué tipo de persona o bueno, con qué características se realizaron estos modelos. Sí que no, pero can you hear me?
Yeah.
Okay, so my question is regarding basically to which type of person you based all of this modeling into. As I understand in my little expertise on this topic, there are several ways that and characteristics that people walk, lay their support into. What kind of what kind of characteristics do you based all of this model?
This here is based on ISO standard loading cycle used in a hip simulator. So when you create an orthopedic device, you have to test it very rigorously under certain conditions. So this is your load and speed cycle that would conventionally be done. So I've just used a sort of very averaged out model. And there's even capacity using this to introduce variations of geometry, loads and speeds, and all sorts of other parameters to create more of a sort of statistical representation of these outcomes. And that's something that definitely needs to be done, particularly driving the shape of this through imaging.
So the variations can affect the results from the simulation, right?
Yes, 100%. Yeah. So there's a big change that can be seen. And one of the things is that because this is just an input, what some of my colleagues are working on is they take image capturing, video capture of people walking, and then they use that to derive the biomechanical loads for a particular individual. So they do this in like football teams and things to try and tell them how to run better. But they also do it for patients who have the potential of needing a hip replacement, for example, to try and see whether they show the same size as people that have degenerative conditions. So eventually we'll replace this for a specific load cycle for an individual with a specific geometry and look to see over a range of parameters for, say, materials, what the responses are likely to be.
Thank you.
Bueno, muchísimas gracias a todos. Gracias por venir, que tengan una feliz tarde. Thank you very much to be here.